Okay, so today we're going to continue our journey into calculus as we talk about more about the derivative with increasing, decreasing, and stationary points. So you guys are going to learn how to use the first derivative today to find stationary points and also where the function is increasing and decreasing, okay? But before we do that, I need to make sure you guys understand what is increasing and decreasing, okay? First off, with increasing and decreasing functions, on an interval where the function is increasing, an increase in x produces an increase in your y, okay? So basically, as x is increasing, y is increasing as well, okay? That's what it means to increase. However, on an interval where the function is decreasing, that means that when x is increasing, it produces a decrease in your y, okay? So again, as x is increasing, as x is getting larger, because as you know, whenever we read a graph, we read from left to right. So if I start over here at negative infinity, as I continue to go to the right, I'm increasing in my x values. So no matter what, x is always going to be increasing. But to determine whether or not the function is going to be increasing or decreasing, you have to look at the y's, okay? So as you read from left to right, on this particular graph, this particular example, what's happening to the graph? Is it increasing or decreasing to start? It's decreasing. It's decreasing all the way to what? One negative one, that point, okay? And then after that point, it's doing what? It's increasing until 5, 2. And as we can see, x is continuing to increase. Our y's are getting larger. I'm going basically from negative 1 all the way up to positive 2 of my y's. After this point, what's happening? So that means it's decreasing. That means it's decreasing afterwards, okay? And when we talk about increasing and decreasing, we reference it as an interval, okay? And when we do our intervals, we only use our x values to represent those points of increasing and decreasing. So as we can see here in the yellow, it was decreasing. And when we identify that interval, we use the x values to represent where it's decreasing. So it's decreasing from what x value until what x value? What's that far left x value? Negative, it'll be negative infinity, far left. Because remember, all the way back up here, it was coming from negative infinity on our x-axis, and then it was continuing to decrease all the way into what x value? Positive 1. So then we would write it like so to represent that it's decreasing from negative infinity to positive 1. The graph is going down along that part of the x-axis. We only use the x values when we are talking about increasing and decreasing. After that, in the pink, as we can see, we were increasing from what x value to what x value? 1 to 5. And then afterwards, we were what? Decreasing from 5 to positive. So we went back to decreasing from 5 to positive infinity. How do I connect these two intervals? With that union. Okay? Just like how we would if it was domain and domain, it's the same type of concept. Except this time we're just talking about where the function's increasing and decreasing. Does everybody understand this concept? Because if you don't understand what I mean when I'm talking about increasing and decreasing, you're not going to understand half of the lesson today.
I understand it.
Okay. Good. Now, if you notice, I use parentheses this entire time, okay? I use parentheses around the 1 and parentheses around the 5 because at 1 and at 5, it's neither increasing nor decreasing, okay? It's neither increasing nor decreasing. We'll talk about that a little bit more as we talk about the lesson today. Now, if your function, f of x, is increasing from A to B, and A to B basically represents an interval of X values, is increasing if the first derivative is greater than 0. So that's how we can use derivatives to determine if our original function is increasing if the first derivative is greater than 0. And vice versa, we'll know that our function is decreasing on an interval from A to B if the first derivative is less than 0. For all my x's on A to B. Because what is the first derivative? What's the first derivative associated with?
Tangent.
Tangent. Okay. Our tangent lines. What specifically about our tangent lines? The gradient. So we're talking about the slope. So if the slope is positive, that means it's going up. That means the graph is going to be increasing. But if the first derivative, if the gradient of the tangent line is less than 0, that means it's negative. So that means the graph is going down. That's the association with it. And we use a sine diagram with the derivatives to find these different intervals. And so we're about to do that now. So we're going to find intervals where the following functions are increasing or decreasing. Okay? So again, in order to do this, we need the derivative. We need the derivative of negative x to the third plus 3x squared plus 5. Find the derivative of negative x cubed plus 3x squared plus 5. Somebody online, give me the derivative.
Negative x squared plus 6x.
Close. I heard negative x squared plus 6x. I'm missing something in front here.
3.
Negative 3x squared plus 6x. I don't know if you said it, but I only heard that x squared and the 6x. So that's the first step. We want to find the derivative, okay? After that, to figure out where our functions are going to be increasing or decreasing, we're going to have to set our derivative equal to 0. We're going to have to set our derivative equal to 0. From here, we need to solve for x, okay? Now this reaches back into our function unit on how to solve these types of functions. Who remembers how we solve these types of functions?
You put the 0 on the other side and you factor it.
What was that last part?
You bring everything to one side of the equal sign and then you just factor it.
Okay. Well, everything's already on one side because it's equal to 0, but we do need to factor it. What's the first thing you look for when you factor? A greatest common factor. Do we have one? An x, anything else?
3.
And a 3, okay? I probably would have done negative 3, but it's fine. If I take out a 3x, I'm left with what on the inside?
Negative x and
So after I factor out my greatest common factor, I can't keep factoring from here. So I said both of my factors equal to 0, and I need to solve. When I solve, I'll get x is equal to 0, and over here, x is equal to, we're doing negative 2 or positive 2? It's going to be positive 2. Okay. Now, these numbers are important. Sometimes you'll see them labeled as critical points, okay? And the reason why they're called critical points is that these are the points that are basically going to separate our function to tell us whether it's increasing or decreasing. So this is what, this is one way to look at it, right? So what we're going to do is we're going to create a number line. That's what I'm going to reference it as, a number line. Some people like to create a table You know, visual aspects, I mean, that's just there. So what I'm going to do is I'm going to put 0 on my number line, and I'm going to put 2 on my number line. The two values I got when I solved my first derivative when it equaled 0. After that, I want to find numbers on this number line that are less than 0, or pick out one number that's less than 0, a number that's in between 0 and 2, and a number that's greater than 2. All of this is to help me determine where my function is increasing and decreasing. So I call them test points. What's the number that's less than 0? -1. What's the number in between 0 and 2? And what's the number that's bigger than 2? 3. Okay? What I want to do with these blue test points is I want to plug them into the derivative. And by plugging these test points into the derivative, it's going to give me a positive number or a negative number. If it gives me a positive number, that means the function is increasing. If it gives me a negative number, that means my function's decreasing. And again, I plug these test points into the derivative. Because remember, the derivative will give us the slope of our tangent line. So if it's positive, that means the graph is going up. If it's negative, it means the graph is going down. So when I plug -1 into my first derivative, do I get a positive number or do I get a negative number? I get a negative number. I'm not necessarily concerned about what the number is. I'm more concerned about the sign of the number. When I plug in a +1, do I get a positive number or a negative number? I get a positive number. And when I plug in 3, do I get a positive number or a negative number? It's going to be negative. This will be -27 plus 18, so it's going to be a negative number. So right here, this sine diagram that I've created, that's with the red 0 and 2 and the blue test points with the blue symbols, this is our sine diagram. It tells us where our function is increasing and where it's decreasing. If it's negative, it's decreasing. If it's positive, it's increasing. So from -infinity to 0, my graph is what? It's decreasing. And why is it decreasing? Why is it decreasing again?
Because when we did the test point and we plugged -1 in, it was negative.
Exactly, because when we did the test point, it's negative. And that means that any value that's less than 0 is going to give me a negative result. I could have picked -5, and I still would have got a negative number. What's happening from, well, I kind of already gave it away. But from 0 to 2, the graph is what? A little louder.
Positive.
That means it is
Increasing.
Increasing.
increasing. Very good. And then what about from 2 until infinity? What's happening?
It's decreasing.
Increasing.
It's decreasing. And that's how you can use derivatives to find the intervals where your function is increasing or decreasing. We take the first derivative, we set it equal to 0. We solve to find our x values, which are called our critical points. We create a sine diagram, and we use test points to determine where our function is increasing or decreasing. and we plug those test points into the what again? We plug them into the derivative, okay? Not the original, because we plug them into the original. Now we're trying to find like coordinates, and we don't want to do that yet. Let's look at this one. Again, we're trying to find.
I have a question for the last one.
Okay, question.
Why was the first one negative infinity and the second one not negative infinity?
Because remember, we're reading from left to right. So all the way on this side of the number line is going to be negative infinity. And then to the right is going to be positive infinity.
Oh, okay.
Yeah. Think about like an XY axis. Far left is negative infinity. Far right is positive infinity.
Okay.
All right. Let's look at B. We're going to find intervals where it's increasing and decreasing. First thing I need, if you haven't noticed, in calculus, we always need the what? We need the derivative, okay? So if anything, if you forget anything else, if you at least know how to find the derivative, you at least got 1 point or 2 points in every problem. As long as you do it correctly, of course. So what's the derivative of 4x to the third minus x squared minus 4x plus 3?
12x squared minus 2x minus 4.
Okay? After I find the derivative, I need to do what with it? By set it equaling to 0 first and then factoring, because this is another quadratic, okay? And this is a great time to review how to factor, like old school X method, quadratics, and slide divide bottoms up. Can't really remember how we went over this before. Go slide divide bottoms up? Okay. But no matter what, we always look for a GCF first before we ever do slide divide bottoms up, the X method, or anything. So, is there a GCF here? There's a 2. When I factor out the 2, I get a 6x squared minus x minus 2. And I said this is a great time to review factoring because, well, I think some of you guys are still taking SATs and ACTs, right? So this is good. Whenever there's an A value, like there is here, remember you gotta slide it. You gotta multiply that number to the last number. Multiply A and C together. What's 6 times negative 2? So remember, you're looking for 2 numbers that multiply to give you negative 12, that add together to give you negative 1. What we're doing right now is I'm using this opportunity to review factoring with you because you might need it to solve a problem to help you figure out the intervals where the function's increasing and decreasing. So we're taking a mini detour of factoring this to basically solve to find the numbers I'm going to put on my Sine diagram. What 2 numbers multiply to give you negative 12 that add together to give you negative 1? So remember, we write that as x plus 3, x minus 4. But because we originally multiplied by 6 at the beginning, we have to divide both of these numbers by 6. Does 3 over 6 reduce?
Yes.
To what?
1/2.
What about 4 over 6? Does that reduce?
Yes.
2?
2 over 3.
It's important that you reduce these. If you don't, you forget about a few things. Don't worry, I want to make sure I take care of that 2 in just a second. We just did the divide part. Now we have to bottoms up. Remember, anytime it doesn't go in evenly, we have to bring the bottom up in front of the x. So 2x plus 1 and 3x minus 2 is what 6x squared minus x minus 2 factors down to be. And then I just bring that 2 on the outside. So now that we have our factors, we are going to set them equal to 0 and we're going to solve. Remember, these are the values that we're going to put on our number line. So I'll have 2 is equal to 0. 2x plus 1 is equal to 0, and 3x minus 2 is equal to 0. Now, first off, 2 equals 0 is nothing, okay? You're not going to get a solution there. But over here, at this 2x plus 1, you'll get x is equal to a negative 1/2. And over here, you get x is equal to a positive 2/3. Those are going to be the values you're going to put on your sign diagram, aka your number line. I do use those two words interchangeably, so please don't get confused if I use sign diagram or number line. They're the same thing. Now I need my test points. Remember, my test points are what's going to help me determine where the function's increasing or decreasing. What's the number less than negative 1/2? Less than? Negative 1. What's the number in between negative 1/2 and 2/3? Sure can use 0. Okay? You can definitely use 0. The only time you can't use 0 is if, like when you do your derivative, if you have an x in the denominator, then you wouldn't be able to use 0 as a test point. And then what's a number bigger than 2/3? 1. These values get plugged into the derivative, and we are concerned about the symbol of the number. So whether it's positive or negative versus actually what the number is itself. So figure out if I'm positive or negative on each of these intervals, each of these sections. Okay, so when you plugged in negative 1, what did you get?
2.
So it was a positive number?
Yes.
Yeah? What about 0?
I got increasing.
So you got a positive number here?
Yes.
And then what about for 1?
I got another positive number.
So you got positive all the way across?
Wait, this is for the derivative?
Bro, I got negative.
Yeah, remember you plug your test points into the derivative.
Oh.
Yeah, I got negative, negative, positive.
Oh, okay. Yeah, that's what I messed up. I plugged it into the original.
Okay, so it looks like we need to double check how you guys are plugging this into your calculator. Remember, when you plug in a negative number, make sure you include parentheses. This should have given you a positive 12, a positive 2, and then a negative 4 when you plug negative 1 into the derivative, which is a positive number. So this should have been positive here. When you plugged in 0 into your derivative, you should have gotten a negative number. Then when you plugged in a positive number, a positive 1, you should have gotten still a positive number. So it should have been positive, negative, positive. Be careful how you guys are plugging this into your calculator because it's the derivative. Make sure you plug it into the derivative. So now that we have that, let's give me my intervals. Reading from left to right. So from negative infinity all the way to positive infinity. To start, the graph is what? It's increasing from
negative infinity to negative 1/2.
Very good. Then after negative 1/2, it's what?
Negative 1/2 to positive 2/3.
It's decreasing. And then what happens after 2/3?
It's 2/3 to infinity.
It's increasing from 2/3 to infinity. So I connect those intervals with the union, and I have from 2/3 to infinity. We write that in the interval notation, always using parentheses because at negative 1/2 and at 2/3, there's something that's happening that we're going to talk about in a second. Plus, from negative infinity to positive, negative infinity and positive infinity, we can't define those, so we're always going to have a parenthesis around those. The only time you'll have a bracket, a square bracket, is if you have endpoints, because the graph is starting at a particular value and ending at another value. Questions on increasing or decreasing before we move on to stationary points? So stationary points. Stationary points are when the function, stationary points of a function is a point where the first derivative is equal to 0. You know those values that are called critical points? They're also called stationary points. So all those values that you get when you set the derivative equal to 0 and you solve, those values are called stationary points. I also call them critical values. Depending on where you go, what you look in, it has both names, okay? Now, at these different values when the first derivative is equal to 0, you can either have a local minimum, you can either have a local maximum, or you can have something that's called a stationary inflection. So when you set the first derivative equal to 0 and you solve those x values, there's either going to be a local minimum there, a local maximum there, or a stationary inflection. Okay? Now, first off, a local maximum, what that looks like is like in your graph, there's it's a hill, okay? And at that respective value, whatever that x value is, there's a maximum there. On a sine diagram, what that means is that at whatever that value is that you get when you set the first derivative equal to 0, if it goes from positive to negative on your sine diagram, that means you have a maximum there. A minimum is when you have a little valley, okay? And that value is the opposite on your sine diagram. It'll go from negative to positive on your sine diagram. And remember, sine diagrams are associated with your first derivative. These are talking about the slopes of the tangent lines. And so as you can see, the slope of the tangent line is positive, slope of the tangent line is negative, or negative, then positive. That's where this whole idea concept is coming from, okay? Now a stationary inflection though, that's when you have like, it is a value you get when you set the first derivative equal to 0, but the graph like looks like this, or the graph looks like this at that value of A, okay? Like you still have that like tangent line that's still horizontal. That happens on your sine diagram when it's a positive and a positive, or it's a negative and a negative. That's what your sine diagram can look like. So it is possible to get a positive, positive, or a negative, negative, but you also want to double check, make sure you're not messing up and plugging your test points into the wrong thing, okay? But if you go from positive to negative, you have a maximum, negative to positive, you have a minimum, and then of course, your stationary inflections are when they're both positive or both negative. Just make sure you guys are understanding when you look at this last example that we did, negative 1/2, it went from a positive to a negative. So at negative 1/2, what's happening on the graph? There's a maximum. And at 2/3, I'm going from negative to positive. So I have a minimum at 2/3, okay? So the first derivative tells you a lot of stuff. Not just necessarily the gradient of your tangent lines, but it also can tell you where you have your maximums and minimums, where your graph is increasing and decreasing, or if you just have an inflection point. So let's look at example 2. We're going to find and classify all stationary points of this function here. And as before, we need the derivative. Somebody online, give me the derivative.
Three x squared minus 6x minus 9.
Very good. And remember, to find our stationary points, the same way we found whether our function was increasing or decreasing, we have to set the first derivative equal to 0 and solve. So this is another quadratic. First thing we should look for is a GCF. Do we have one?
Yes.
3. So that'll give me x squared minus 2x minus 3. This one's a tad bit different than the other one because we don't have to slide divide bottoms up because our a value is a 1 now that I factored out that 3. So now I'm just looking for two numbers that multiply to give me,
-3.
that add together to give me,
-2.
and what are those numbers?
-3. 1.
So this factors down to be x minus 3, x plus 1. Then I'll set each of my factors equal to 0. As we know, x equals 0 is not, or I'm sorry, 3 equals 0 is nothing. But over here, x will equal,
3.
and x will equal -1. So remember, when you set your first derivative equal to 0 and you solve, you're finding potential stationary points, maybe a stationary inflection point. I just call them critical points just because it lumps everything into one. Let's do this sine diagram. -1 comes before 3 on a number line. Remember, negatives come before positives in a number line. Don't get them switched. Otherwise, you're going to end up with a weird number line that you got to try to make sure you do correctly if you want to get the correct answer. I need a test point less than -1. I need a test point in between -1 and 3. And I need a test point bigger than 3. 4. Now remember, I just need any point that's in each of those intervals. It could be any number as long as it falls in those intervals, because the result is going to be the same. And I plug each one of those test points into the, so go ahead and do that. Careful. Plug it into the derivative. Here we go. So when I plug in -2, what did you guys get?
Positive.
Positive. When I plug in 0, we got,
Negative.
and then 4, we got
Positive.
positive. So remember, not only does the sine diagram tell us where the function is increasing and decreasing, but it also tells us our if we have maximums, minimums, or stationary inflection points. So at -1, what is happening here? What do we have at -1? If it's positive on the left-hand side, then negative on the right-hand side, it's a what?
Maximum.
It's a maximum. And then what about at 3?
A
Minimum.
minimum.
It's a minimum because I'm going from negative to positive. So I have a maximum at the x value of -1, and I have a minimum at the x value of +3. These are coordinates on the original graph. How do I find the corresponding y values to go along with them?
Plug the x values back into the original function.
Plug the x values back into the original function. So do that now. I'm actually finding the coordinates now of my maximum and minimum just to go that one step further, because more than likely you'll have to find the coordinates of the maximum versus just determining what it is, okay? So plug -1 into the original, plug 3 into the original. So for the y value for the maximum, we plug -1 into the original. Remember, anytime we're looking for a y coordinate, we always plug it into the original. So when we plug -1 in, we get a +10. And then we plugged in 3, we got a 22. So these are the coordinates of your maximum and your minimum. Very rare they'll ask you for like just to classify what it is. I just wanted to kind of go that additional step. But yes, we have a maximum at -1 and a minimum at 3. And you kind of see how the graph looks a little bit, right? It's increasing, decreasing, increasing. That's what a graph will look like. Okay. Okay. Find the greatest and least value of y equals the function on the interval from -2 less than or equal to x less than or equal to 5. So this one here, we have endpoints, okay? And we're trying to find the least and greatest value of y. So in other words, we're trying to find the largest y value and the smallest y value, okay? To do that, just like before, we need the derivative. So I'm going to use dy dx. Remember, this is another way to represent derivative because I have a y here. What's the derivative of x to the third minus 6x squared plus 5?
3x squared minus 12x
We have to set that,
equal to 0.
and then we solve.
Yes.
Is there a GCF?
Yes.
3x.
So when I factor that out, I'm left with n.
X minus 4.
Very good. And I'm going to set both of those equal to 0. And these are my crucial points here, okay? Now the thing is that it's asking me to find my greatest value and my least value. So that means on the original function, which one of these x values is going to give me my largest y value and my smallest y value. I'm not necessarily concerned about if it's a maximum or a minimum, because if I were to plug these values into my original, it's going to give me a large value or a small value, okay? However, I have endpoints here. I have -2 and I have a +5. So it's very possible that when I go and it's very possible that my largest y value or my smallest y value could occur at the endpoints. So when we go and we plug in our critical points, the 0 and the 4 into the original to find their corresponding y value, I also need to plug in my endpoints as well. Because again, my endpoints could be the lowest y value or it could be the largest y value on this particular interval. So what I need to do is I need to take those critical points of 0 and a 4 and I need to plug them into my original function. But I also need to plug in -2, that first endpoint, and +5, my second endpoint, to see if they give me potentially the greatest y value or the smallest y value. So go ahead and plug in each of these 4 values into the original function. What do we get when we plug in -2?
What did I get?
Yeah.
Negative.
-27?
Yes.
Yep.
What do we get when we plug in 0?
5.
5.
Good stuff. What do we get when we plug in 4?
-27.
And we plugged in +5.
-20.
Okay. So remember, we're plugging in our endpoints and our critical points, the 0 and the 4, into our original function to figure out which one's going to produce the largest y value and the smallest y value. And as we can see, we actually have the smallest y value at 2 different places, at -2 and at 4. So at x equals -2 and x equals -4, the least value is -27. And then our largest one occurs at 0, and the greatest value there is 5. And we know those are the lowest values and the highest values because remember, 0 and 4 represent critical points. They represent maximums and they represent minimums. So if we have a maximum or a minimum at these respective values here at 0 or at 4, then that means that that's like the highest point that the graph is going to go or the lowest point that the graph is going to go. We just have to test our endpoints because it's possible at 5 it's higher or -2 is higher and vice versa. Okay? So essentially, you're here at -2, -27. You're at 0, 5. Then you're at 4, -27. And then you're at 5, -20. I don't know why I wrote this so far out. But essentially, your graph looks like this. How do I know? Well, if I were to do a number line with those critical points, I would see that. Okay? I would see that there's a maximum at 0 and a minimum at 4. And I did make a mistake. That should have been a +4, not a -4. Thank you for the catch. Because that x value was a +4. Thank you very much. All right. Questions on using the derivative to find where the function is increasing, decreasing, stationary points. No inflection points yet, but remember that's when you go positive, positive, or negative, negative on your Sine diagram. Let's spend about 15 minutes practicing just to make sure that we are fully good. Okay? So these problems here, you don't have to write down. I just kind of want to make sure that everybody's good. Okay? So let's give this one a try. So don't forget, for a problem like this, it says find dy dx when the equation of the curve is y equals -x³ plus 4x² plus x minus 4. Section of the curve is shown to you. As we can see, if this is the original graph, then our local maximum should occur somewhere in between 1 and 4, yes? Based off of the graph. So let's find our derivative. What you guys get for the derivative?
-3x² plus 8x minus 1.
-1 or +1? That makes a difference.
+1.
Be +1, because it was a positive x. Okay? And so it says to write down the coordinates of the local maximum. Here, we will set this equal to 0. But if you notice, when I multiply -3 and 1, there are no two numbers that can multiply to give me -1 that could add together to give me 8. So don't forget, you can also use your calculator to find these x values. Okay? Don't forget about that as well. Go into your graphing feature. So go into y equals, plug the left side into y1, right side into y2, and see where they intersect to find those x values. Okay? So I'm going to plug in -3x² plus 8x plus 1, and then I'm going to plug 0 into y2, so then that way I can see where those two intersect. Okay? So this quadratic is coming in blue.
Wait, what did you said the derivative as y1 and 0 as y2?
Yes, because I'm trying to find those x values. I'm trying to find those critical points. So as we can see, I have 2 here, which makes sense. So I'm going to find out what they are. Second trace, intersect. Remember, since I have 2 different intersection points, I want to get to the one that's closest to the left. I click enter 3 times. And I can see one of those values rounded to 3 significant figures would be what? $120. Because remember, it was -0.1196. The 6 rounds to 9 up, 9 rounds to 1 up. So we have that one. And then I have to find the other one. Go back through the same process. Second trace, option 5. Move closer to the second intersection point by clicking the right arrow button over and clicking enter 3 times. Don't forget, that's also featured. Remember, you're not without your calculator for the entire test. So, I mean, we could have also done it on the other problems as well. But I mean, I think factoring was a little bit easier than trying to do all of this in our calculator. In my opinion. Round this to 3 significant figures. What do you get?
2.79.
2.79. So 2. Okay. So one of them is the local maximum. Which one is the local maximum? Is it the negative number or the positive number? It's the positive, because again, the maximum occurs in between 1 and 4. So it's not this one, but this one. And it's asking me to write down the coordinates. So I can take this value and I can plug it back into the original to get my corresponding y coordinates to answer this question fully. Okay? To answer this question fully. All right? Not gonna do that because I wanna make sure I try to get through as many problems as I can in the next 15 minutes. But I will also say that again, you are allowed to use your calculator the entire time. So if you wanted to, we could have plugged in the original function graphed it, and we actually could have figured out where that maximum was using our calculator. That's not cheating or anything like that. It's just using all of our resources. So how do I find that maximum point? I go back to second trace, and I go to option 4, which says maximum. I go to the left side of the maximum for left bound, any point that's on the left side. And then it says right bound, I go to any point that's on the right side of the maximum. And I click enter. And I let all the calculator do the work for me on guess. And there it is. There's that x value that we came up with when we did it using derivatives. And there's the corresponding y value. So that would be 8.21. That's another option for you. It doesn't specify which option to use, so you can use either one to your benefit. However, if it does say use derivatives or show or something, you have the algebraic way to do it. Let's look at this one. For which point on the graph of the function f of x shows that f of x is less than 0 and f prime of x is greater than 0. So out of these 4 points, A, B, C, and D, which one of these applies to this? How do you know that it's that point?
Well, the first thought I had was it's a positive gradient, so the tangent of the gradient of the tangent would be above 0. And I thought about how it's a negative y value, so it would be less than 0.
That's exactly what I would have said. So because this f of x is less than 0, it's basically saying that your y values have got to be negative. So automatically that eliminates A. And then it says f prime of x is greater than 0. Remember, f prime of x means derivative. Derivative needs the slope of your tangent line, the gradient of your tangent line. So it needs to be positive. If you look at B, the gradient is negative. And at D, that tangent line gradient is negative as well. So both of these are out. The only one left is C. Very good. Don't want to do that one. I already did one like that. Oh yes, let's do this one. So the function f of x equals 2x to the third plus px squared plus 2 has a local maximum at x equals negative 2/3. What is the value of p? If there is a local maximum, what does that mean? Huh? That means there's a point, and Christian held his pencil where it was like this, where it was flat. What does that mean? If it has a local maximum, that means it looks like this on our graph. And it's saying at x is equal to negative 2/3. In today's lesson, how did we find local maximums? What did we do to find them? We used the derivative. What else did we do?
We factored the derivative.
We factored it after we set it equal to 0. And then we solved it to figure out the x values that gave us either a maximum or a minimum. But since we already know that our x value is negative 2/3, then we already have that part of the solution. The one thing is that you have to associate with when you see local maximum is that you set your first derivative equal to what number again? You set it equal to 0. Because that's what we did in every single one of these other problems. We set our first derivative equal to 0 to try to figure out our local maximum. We set our first derivative equal to 0. Not on this one. We set our first derivative equal to 0 to find those points here to determine if we have maximums or minimums. Then we solved it to find our x value. But in this particular problem, we're already given that our x value is negative 2/3. So if we were to set our first derivative, which you said you guys got 6x squared plus 2px. If I set that equal to 0 and plug in the fact that I already know that x is equal to negative 2/3, I can find my value of p. So in this particular problem, we were pretty much working backwards because we already knew what x was if we were to solve this out. We just had to plug it back in to the derivative to help us figure out the value of p. Not the original, because remember, if we plug an x value back into the original, we're getting a y value. And right now, I don't even have p to even find an original y value. So when I do this out, I'll get 6 times 4/9 minus 4/3 p. All I'm doing is multiplying. What's 6 times 4/9? It's 24/9. How do I solve for p? I write too big. So you said something about subtracting. So if I take 24/9 and subtract it over, how can I solve for p?
Divide negative.
Multiply by the reciprocal. So multiply by positive 3/4.
Not positive 3/4. Do negative 3/4 because you're trying to get rid of that negative 4/3. So if you multiply by just the reciprocal, not the opposite reciprocal, everything cancels out.
Okay.
So then p would equal what number? What is that? What's negative 24/9 times negative 3/4? How many times does 4 go into 24? What's 24 divided by 4?
6.
6. What's 3 divided by 9?
3.
Or 9 divided by 3? 3. What's negative 6 divided by negative 3?
2.
P is 2.